Good day to everyone watching this video presentation. We are going to present about our project, which is the application of calculus in physics, specifically about electromagnetic induction. My name is Siti Norsyaqilla binti Muhammad Nagui. I would like to present the introduction about physics. What is physics? Physics is a basic science that study of matter, motion and energy. The word physics comes from an ancient Greek word that means knowledge of nature. Physics looks at how everything around us behave and try to find the explanation, and that's why it's claimed that there must be some fundamental rules that govern everything around. In others words, physics is like an applied mathematics where the basic mathematical concepts and calculations that apply them in physics to prove the theory and law. Some of the important people that involved in this discovery of physics is Archimedes, Sir Isaac Newton, and Ibn al-Haytham. The relationship between calculus and physics. Firstly, physics is related to calculus by using a calculus as a mathematical tool in order to understand and solve the problems. In physics, the calculus can be represented as the dsdt and dvdt. It is being said that the distinction between both of them is a little. As an example, the geometry is the branch of the mechanics.
Hi, my name is Nurul Nadiah binti Azhar. I would like to present about the key concepts. What is Faraday's law? Faraday's law of electromagnetic induction, also known as Faraday's law, is the basic law of electromagnetism, which helps us to predict how a magnetic field will interact with an electric circuit to produce an electromotive force, EMF. This phenomenon is known as electromagnetic induction. Now, let's move to the Faraday's law formula. The induced electromotive force, EMF, in a coil is equal to the rate of change of flux linkage. The flux is the product of the number of turns in the coil and the flux associated with the coil. The formula of Faraday's law is given below. Induced electromotive force, EMF, equal to number of turns multiplied by rate of change of magnetic flux with time. Self-inductance. When an electric current is passed through an isolated conducting coil, it gives rise to a magnetic field in the coil so that the coil itself behaves like a magnet. The magnetic flux produced by the current in the coil is linked with the coil itself. The definition of the self-inductance is, as the strength of the current in the coil is changed, the flux link with the coil also changes. Under such circumstance, an EMF is induced in the coil too. Such EMF is called a self-induced EMF, and this phenomenon is known as self-induction. Next, self-inductance formula. Self-inductance formula is given as induced EMF, E, equal to the inductance, represented by L, times rate of change of the current by times. The minus sign indicates that a changing current induces an EMF that is in opposition to that change. Self-induced EMF is also called back EMF.
Good afternoon, Doctor. My name is Nurainina Izzati binti Rosdi, with transcript number 280541. So, I'm going to present about the methods that's used to solve the problems in electromagnetic induction. So, for the first method, we use a derivative method. The method of computing a derivative is called a differentiation. In simple terms, the derivative of a function is the rate of change of its output value with respect to its input value. The figure shows the rules of the derivative that we use in calculus. Relate to the Faraday's law of induction, it says that the induced EMF around a closed loop is equal to the instantaneous rate of change derivative of the magnetic flux through the loop. Now, I will explain about how this method can be used in this electromagnetic induction. The induced EMF in a coil that has n loops produced by a change in flux in a certain time interval is given by negative n d theta over dt. The flux through a loop of area A is given by PA cos theta. By applying the calculus and taking the derivative of the cosine to get the sine, it's easy to show that the EMF equation can be expressed as NBA omega sine omega t. The second method, we use a differential equation method. In calculus, a differential equation is an equation that relates one or more functions with their derivatives. While in applications of calculus in physics, the functions generally represent physical quantities. The derivative represents the rates of change, and the differential equation defines a relationship between these two quantities. We can use the differential equation method to solving the problems in self-inductance. The equation below is about the combination of change in current and magnetic flux from Faraday's law and Lenz's law equation. we can use this equation and apply with differential equation method so that at the end, we can prove to get the solution of the problems.
For example and analysis section, our group has two examples to illustrate the key concept of our term. Example 1. A 215 turns planar coil with a surface area of 25 cm square is placed in a uniform magnetic field V of 2.05 Tesla. Initially, the plane of the coil is perpendicular to the field. The coil is then rotated about an axis perpendicular to the magnetic field with a period of 0.16 seconds. We need to derive a formula for the induced EMF in the coil at time t. From the Faraday's law, it states that induced electromotive force in the conductor is directly proportional to the rate of change of the magnetic flux linkage in the conductor, and we will get a formula with E equals to d lambda over dt, where E is electromotive force and d lambda over dt is rate of change of magnetic flux linkage. From the formula, we can substitute lambda equals to MBA cos theta, where n is the number of turns of the coil, B is the magnetic field strength, and A is the surface area in unit meter square, and theta is the angle between the magnetic field and the perpendicular line of the planar coil. And we can substitute theta with omega t, then substitute omega with 2 pi f, then we substitute f with 1 over upper t. And we will get a formula E equals to negative 2 pi over upper t multiplied with MBA sine 2 pi t over upper t. From the formula, we can substitute the value given, which n equals to 215 turns and B equals to 2.05 Tesla, and the A is 25 times 10 power of negative 4 meters square, and sine 2 pi t over the period 0.16 seconds. And we will get the induced electromotive force formula, which is equals to negative 43.27 sine 39.27 t. And we can substitute the value of t, 0.1, 0.2, 0.3, 0.4, and 0.5. Then we can get the magnitude of the induced EMF in time t. And for this example, we will ignore the negative sign because we only need to get the magnitude of induced EMF, and the sign is for the direction of the EMF. Example 2 is about self-induction. A constant EMF of 1.04 volt is induced by a changing current in a coil of inductance 0.26 Henry. The initial current is 13 ampere. After 2 seconds of the supplying current, we need to calculate the current and the magnetic flux linkage in the coil. So from the formula of self-induction, L equals to negative E over di over dt, where negative E is back EMF induced in the coil, di over dt is rate of change of current in the coil, and L is self. From the formula, we can derive the rate of change of current. Then we will substitute the value given, which is 1.04 volt and 0.26 Henry. Then we will get the rate of change of current is negative 4 ampere per second. And after 2 seconds of current, we use the formula I equals to initial current plus the rate of change of current multiplied with the time taken. And we substitute the formula, the value given, then we will get the current after 2 seconds is 5 ampere. Now we will use two formulas, one from self-induction and one from Faraday's law formula. And we will compare these two formulas, and we will do integration both sides by using the differential equation method, and we will get the formula Li equals to lambda, where L is self-induction, I is current, and lambda is magnetic flux linkage. And we will substitute the formula given, and we will get the magnetic flux linkage after 2 seconds is 1.3 Weber. And these two are the example we given for our electromagnetic induction term.
For our project is we can determine that physics is also amazing because we can relate it with our life. Calculus and physics have a strong relationship. Calculus is a mathematical tool that used by understanding the physics, and calculus is used to solve the problem of physics. Key concept of our project is the Faraday law, and the method that we use to calculate electromagnetic induction is derivative and differential. Differential calculus are widely used in physics. We are used derivative and differential to apply the key concept needed. For our result of example, the first example is electromagnetic force equal to negative 43.27 sin 39.27 t. And for the second example is current equal to 5.0 and magnetic flux is 1.3. Thank you for watching our video presentation.